Hello again. So in the previous video, I showed you that for a cantilever beam, you can use the integration method based on the differential equation of the elastic curve, which is EIY double prime equal M, and figure out the maximum deflection at where the load is applied. Or actually, you could get the equation of the elastic curve Y as a function of X. By the way, just note that positive X is taken as this direction and positive Y is up. Now, the way I determined this for you was based on cutting the beam and using the left side to figure out the moment, internal moment. What if we decided actually to use the other side? So in other words, cut the beam right there, but take X to be taken from this side. And let's go and try to find internal moment, shear and moment. Of course, we don't care about the internal shear, and actually internal shear should be, the positive should be up, even though it's not really important in this case, because we're looking for the internal moment. Okay, let's go ahead and find the moment as a function of X. So remember, all you need is this moment, and then you can start integration. So, taking moment about this point, call it point O, right? Let's say if clockwise, for example, is positive. So we start with M, and the moment of P is going to be also positive, Px. That's it. M equal minus Px, which is totally different than in the previous video when we used the left side. Anyways, this is also valid for the whole length of the beam. Now we can start our integration. So EIY double prime equal M, that's minus Px. So we go ahead and integrate once, and that gives us the equation of a slope, y prime. So we get minus Px squared over 2 plus C1. So what is the boundary condition? The obvious boundary condition is that x equal L, remember x taken from here, this is x equal 0, and x equal L is right here. We know that the slope is 0. So if we go ahead and set the slope equal to 0 and put x equal L, this time we do actually get a C1 equal PL squared over 2. So now the equation of our slope is EIY prime, right, equal minus Px squared over 2 plus PL squared over 2. So that represents the slope of the elastic curve based on the x taken from this side. All right, let's go ahead and integrate one more time and get to the equation of the elastic curve, the deflection. So this time we get minus Px cubed over 6, right, plus PL squared over 2 times x plus another constant of integration. This time our boundary condition is what? Also at x equal L, y is 0, right here. Deflection is 0. So if you put y equal 0 and x equal L, we get minus PL cubed over 6 plus PL cubed over 2 plus C2. And if we try to solve for C2, we get a 1/6 minus 1/2 PL cubed. 1/6 minus 1/2 is minus 1/3. So minus PL cubed over, actually minus just PL cubed. Sorry, I was thinking of EI. Let me just get rid of that. All right, PL cubed over, PL cubed over 3. I'm thinking of something else. Anyways, so now we are ready to get the equation of the deflection. So EIY is equal to what? Minus Px cubed over 6 plus PL squared over 2x minus PL cubed over 3. So this is the equation of the elastic curve, this curve, this is the one here, based on the fact that x is taken from right here. So now let's test it. So maximum deflection happens where? Maximum deflection happens at x equals 0, right here. So if we set x equals 0, y becomes, so this is gone, so it becomes minus PL cubed over 3I, which is exactly matching this guy that I got here. So you see, it didn't matter which way we cut. Well, we cut the beam somewhere, but which way we took the x. Of course, the equation of the moment is going to be different, but the end result is going to be the same. But let me now just go ahead and show you something else. So let's go to a different beam. So let's say now we have a simple supported beam, right, with a uniformly distributed load, W acting on it, over a length L, right? And our objective is to find the deflection, maximum deflection, which obviously is going to happen because of symmetry right in the middle, right here. So we want to find Y max. And of course, the answer is going to be in terms of the parameters that we have, W and L. All right. So let's go ahead cut the beam and find the equation of the moment. And then, of course, we're going to say EIY double prime equal M. So first, we know that the reactions here are going to be half of WL, because remember that the concentrated load in the middle would be WL, right? So half of it will go to each side. All right, cut the beam. Right? And they have an internal shear, an internal moment. Remember, this is taken as x. Let's go ahead and take moment about here to find that internal moment. So sum of the moment about O equals 0. Let's take counterclockwise as opposite. So we start with M. The moment of WL over 2 about that side, point O would be WL over 2 over, times x. And then the moment of the Wx times x over 2 would be positive, equals 0. So moment becomes minus Wx squared over 2 plus WL over 2 times x. And this is valid for the entire length of the beam. So we are ready to go to our differential equation. So this is M now, right? EIY double prime equal M. And start by integrating. So EIY prime would be our slope first. Equation of its slope would be minus Wx cubed over 6 plus WL over 4x squared plus a constant of integration. Now, if you don't see the obvious boundary condition, which because of symmetry, you could see that actually the slope is 0 here at x equal L over 2. It's okay. You can continue integrating and get both C2 and C1 and C2 in the same equation. But the two other obvious boundary conditions are at x equals 0 and at x equal L, deflection should be equal to 0. But let me actually use this boundary condition, which is at x equal L over 2, slope must be equal to 0. So if we set this equal to 0 and x equal L over 2, we end up getting minus WL cube, I believe 48, and then WL over 16, I believe, also L cube, right? Let me erase this guy here. All right, and plus C1. So C1 becomes 148 minus 116. 148 minus 116 is 2 over, I believe, 48, which is 24. So I said 1 over 48 minus 116, so that becomes minus WL cube over 24. Okay, so the equation of our slope becomes EIY prime equal minus WX cube over 6 plus WL over 4 x squared minus WL cube over 24. Let's go ahead and integrate one more time. Let me move up here, guys. Sorry. And second integration will give me EI y equal minus WX cube. So we're integrating, so WX to the power 4 over 24 plus W L x cube over 12 minus W L cube over 24x plus another constant C2. What is the obvious boundary condition? At x equals 0, y is 0, which actually makes things easier for us. So then if y is 0 and x is 0, C2 becomes 0. So here we go. The equation for our deflection curve becomes EIY equal minus W x to the power 4 over 24 plus W L x cube over 12 minus W L cube x over 24. I remember C2 is 0. So maximum deflection happens at x equal L over 2, and I believe I haven't done this calculation. I should have done this before I started making this video. But anyways, y becomes 1 over EI. I believe it becomes 5 WL to the power 4 over 384. You can check on that, but I'm pretty sure that's what's going to be the outcome when you put L over 2 in place of x. Okay, if I'm wrong, I'm going to come back and correct myself in the next video. I'm making this video one after another, and I'm really pressed for the time. So hopefully this is the right answer, and I'll check it in a few minutes. Thanks for watching, and this should be the last lecture for tonight. So altogether it should be 3 lectures, 1 from chapter 9 and 2 from chapter 10. Thanks.